Hi, everyone. I'm Joel. I'm co-founder of a startup called Canvas. We're building a framework for peer-to-peer applications. I first got into the decentralized web way back in like 2017, and I was like an undergrad in college, and I remember one of the first things I ever tried to make, JS IPFS had just merged like this experimental Pubsub feature, like flood sub, if people remember that. One of the first things that I tried to make was this chat app in the browser that worked exactly like the universal connectivity demo that we saw Daniel give earlier, right? You open two tabs in different browsers, and then you can like send messages between them. And it was really cool. It felt like amazing, But of course, it works like IRC, where if you close the tab and somebody else sends a bunch of messages, and you come back, you haven't received them, and you don't really have any way of like figuring out or catching up on messages that you missed while you were gone. Also, in general, GossipSub is like really cool. It has some amazing properties. It has like all kinds of engineering that went into it, but it doesn't have like perfect like delivery guarantees. Messages might be dropped, and you need like a message ID function to make sure they're not delivered twice and whatever. And that's just what Pubsub is, right? That's the abstraction. But it's an interesting question to ask of like, okay, well, what kind of primitive would we need to build a chat app that has persistence and has syncing, the one that resembles the chat apps that we're used to, that we actually want to use. So if we're thinking about this example, the persistence aspect is pretty easy. Like we can easily just open key value store or SQLite database and save all of our messages as they're coming in. Save them by like SID or key or whatever we have. The syncing aspect is what's hard. If we have these two peers, Alice and Bob, and for whatever reason they have a different set of messages that they've received, and they get connected to each other, how do they figure out which messages the other has that they don't? There are a few ways that you could imagine trying to approach this. In the first, like most naive case, they can just send each other their entire message logs. That's a lot of data, so we don't want to do that. Maybe it's like months of chat history, right? You don't want to do that. So could we send like just like a log of just the CIDs? Okay, well, even that is probably still a lot of data. And if it's something that we're going to be doing like a lot, like on every new connection or periodically, don't want to do that either. Maybe there's something with like bloom filters we could do, kind of like getting into the weirder ideas. Like, okay, so Alice could send Bob a bloom filter of all of her messages, and then Bob could iterate over all his messages and see which ones don't match, and then send all those back to Alice. Okay, that's interesting, but even that still requires this O of n like linear work on Bob's part, and he has to do this just whenever Alice asks, and that's not really like the balance of like power that we want. Another direction that you could imagine taking is like version vectors, right? This is kind of from the CRDT world. So maybe everyone who's like participating in this chat app like keeps just like a counter, their own personal counter, of like the sequence of message that they're sending, right? And they increment it every time, and then when Alice wants to figure out if she's missed any messages, she asks Bob for all of like the versions for all of the unique peers that have sent messages from him, and then she figures out if any of them are mismatching. And this is like the common approach for like CRDT based applications today, but even this isn't really a perfect solution, because even if everyone follows the rules, it only tells us about messages that might be missing and doesn't necessarily give us a way of actually retrieving them. Like, what if we just find out that, we are missing a message? Who do we get it from? Maybe the person who sent it isn't online anymore, Or do we like keep asking people for this message, asking everyone we know, like until the end of time? And then also, it like means that we're keeping track of this extra state, which grows with the number of peers that are participating in the app. Or maybe we want a chat app where it's like peers are anonymous, or they sign their messages with like some zero knowledge proof of like membership in some set, but they're not actually uniquely identifiable. So it'd be nice if we had some like cleaner separation of concerns and a way for these two peers, Alice and Bob, to efficiently and statelessly figure out the union of the set of messages that they have received. So this is like the goal. Alice has these messages ABD, Bob has ACE. They do something that's quick and fast, and they can do on every connection and periodically that results in them identifying the missing messages. So a completely different approach to this problem uses this exciting new data structure called a Prolly tree. A Prolly tree is a special kind of database index. A thumbs up in the back. Hell yeah, let's go. Prolly tree is a special kind of database index. So it's a Merkle tree. It's a special Merkle tree. I'll explain its structure in a second. It's a Merkle tree that's built over a set of key value entries. So here in the bottom, we have a bunch of entries. The key could be like a message CID or some other like application like message identifier. And then the value is like the content of the message. And conceptually, we start with these as the leaves of the tree, and they're sorted lexicographically by key. So a Prolly tree is this Merkle tree that is built on top of these entries. Right? So here's the leaf entries, and then here's a tree that we build on top of this. And it has this kind of skip list structure. So this doesn't look like a normal tree, right? It's like trees are normally drawn like with like 45-degree angle edges, and these are like rectangular. That's the difference between a tree and a skip list, is one is rectangular and one is drawn with 45-degree edges. I find this like more intuitive to look at. So the significant thing about a Prolly tree is that it has these two properties. It's deterministic and it's robust. The deterministic property means that the structure of the tree, so like how many levels there are and like which parents at which level are the parents of which children, the entire structure of the tree is a pure function of the content of the leaves. So those entries that we started out with, they uniquely determine this like tree structure. It's a Merkle tree, so all of these nodes have like hashes in them too. So all the way up to the root hash, it's a pure function of the leaves. There are a bunch of ways of like building deterministic Merkle trees. The simplest one is just, like a binary Merkle tree, that starts with like that pairs every leaf and then keeps doing that until it gets to the root. The difference with a Prolly tree is that it's also robust. That means that if you make a single edit, let's say we like insert a new leaf into the middle of the tree, right? And then, like redo the deterministic algorithm that like creates the structure, that the entire tree isn't going to shift over like it would with a binary Merkle tree. Instead, almost always, almost all of the tree structure will remain the same. So let's see if I can give a more visible example of this. Okay, so here's two GIFs of a Prolly tree being edited over time. On the left, we have like random inserts, and then the tree is like growing, and on the right, we have like random in-place edits. You can see that like the number of children per node isn't like constant. Like some nodes have like a couple children, some nodes have a lot of children. And you can also see that like every time we make an edit, there's this highlighted path from the leaf up to the root. And those are all the nodes that are changing. So those are all the nodes whose like hashes are changing, right? And you can see that like, on the right, if you look at those edits as they're being made, most of the tree structure stays the same, even though we're changing an element somewhere in the tree. The rest of the tree and the rest of the hashes and basically all the tree except for that direct path up to the root is like preserved. And only in like some cases is there like an extra split or an extra merge that changes like non-local structure. How this actually works, I'll go back a slide here. In case you're wondering how this actually works, the way that you like derive this deterministic but robust tree structure is with essentially a rolling hash. We don't even need a rolling hash in this case since we have these like discrete nodes. So you just have this rule that's like, okay, I'm going to look at the hash of every node, and then if it's less than a certain threshold, then that becomes the first child of a new parent. And if it's not less than that threshold, then it becomes like a sibling of the previous parent. Lots more details there. I have a big long blog post about this that I encourage you all to check out if you're interested in the details of Prolly tree implementation. The upshot of this is that if Alice and Bob both maintain these Prolly trees over their set of messages, so this special kind of like merkleized database index, they're able to perform a very efficient type of Merkle sync. So here we have these two Prolly trees, and there's just one difference between the two. A new element has been inserted right after G here in the bottom row in the lower tree, right? And so the boxes highlighted in red are all of the nodes whose hashes have changed due to this insert. So if one of these is Alice and one of these is Bob, they have a really efficient way of figuring out which element Bob has that Alice doesn't, right? And you can kind of guess at what it is. It's really just like depth first traversal. So they first like exchange root nodes, and if their hashes match, then since Prolly trees are deterministic, they know that their entire database contents are exactly the same. So they exit early. If they don't match, then they go a level down, and Bob sends Alice his 2 level 3 nodes, so the 2 children of his root. And then Alice looks at those, and any of the hashes at that level that match, she can just skip because she knows that all of the children of that node are going to be the same between the two as well. And any that don't match, then they recurse into that. So it's like a depth-first traversal that skips common subtrees. So in the case where there's just one change like this, it only takes like a number of back and forths equal to the height of the tree to figure out which element Bob has that Alice is missing. This is kind of, a toy example to show like the structure of the tree. In practice, we use like a large fan-out degree, like 32 or something. So even for like millions of messages, we only have like at most, 3, 4, 5 like node levels to descend. Let's see. Right, so Merkle sync, depth first traversal, skips shared subtrees. In general, this actually gives you like something like in JavaScript, this would be typed like this. It gives you essentially an async iterable over the differences element-wise or entry-wise in 2 different key value stores. And you can perform this efficiently like over the network. So another neat result here is that like the on-the-wire protocol for doing this Merkle sync is really, really simple. All you actually need to do this over like a libp2p protocol is these 3 different like RPC requests. You just need, Alice needs to be able to ask Bob for his root node, ask Bob for like an arbitrary node in the tree and its children, and that's it. That's, it's Alice's job to kind of like, by initiating the sync to manage the traversal. But the actual protocol is like very, very light, and it's very light on like what it asks computationally of Bob in order to do this like diff iteration. Yeah, so this gives us access to this. It's like a one-sided thing where Alice, syncs with Bob, and then Bob would have to sync with Alice, but it gives us like efficient iteration over missing entries, like so. So in the beginning, I said, okay, we have Pubsub, we have GossipSub. They're interesting, they're exciting. Lots of engineering has gone into making like GossipSub attack resilient and whatnot. That's awesome. But what's conceptually the primitive that would make implementing chat simple? What is like the new primitive that we really want? Because a totally valid response to like the beginning of this would have been to say, Pubsub is what it is. If you want like persistence or sync, that's just like something else. Okay, well, what is that something else? What's like the natural abstraction here? The natural abstraction here is a partially ordered causal log that gives you reliable causal broadcast of events. So this is what it's all kind of building up to. If we want persistence and sync for something like Pubsub, what we're really talking about is a log of messages that have some partial order to them. We'd like them to be delivered and to sync relatively in the order that they were published. We don't need it to be perfect or total, and that would also be impossible, short of a blockchain or something. So short of that, the best that we can do is have something kind of like, this diagram would be familiar to people in CRDT world. The best that we can do is something kind of like a Git repository, where when you publish a message, it's like a commit that points to some number, maybe one or more, of the most recent messages that it's seen, right? That gives it this kind of this kind of growing, flowing graph structure like this. And then one of the cool properties of Merkle sync is that it's guaranteed to yield these in lexicographic key order. What that means is that we can kind of play some tricks with the keys that we use to make sure that that key order reflects the causal order of these messages as they point to their parents. There's a lot more details under here that we could get into, and if that's interesting to you, please come up to me after and we can talk about them all. Eventually what this gets us, so this was also something, Daniel, I think you were talking about with your universal connectivity talk, which is that delivery for operation-based CRDTs is in general an unsolved problem, right? It's kind of out of scope for the CRDT people to figure out exactly how they actually want to deliver their messages. A common constraint that they have is that they need to deliver their messages in causal order, depending on the exact kind of CRDT that they're using. And this structure actually guarantees that. And it does so without requiring people to keep track of these version vectors per peer. It's a pure function of just the databases that Alice and Bob happen to already have. And they can just perform this sync pairwise over a libp2p stream, and they're good to go. So we've implemented this as a libp2p service using the fancy new libp2p services API that just came out. Here's a code sample on the left of eliding most of the libp2p configuration, but there's the services object. This service is called GossipLog, one of the internal components that we have open sourced. So you just add the GossipLog service to your libp2p thing, and then you can append arbitrary messages, arbitrary IPLD values to the log, and then they will be delivered in causal order to this apply function that you provide when you instantiate the log. So internally, this uses Gossip_sub to publish the messages on a topic, low latency. If people receive them and they have all of the dependencies, all of the parents of that message, it'll be delivered to the apply function right away. And if they don't, if they're missing some parents, it'll mempool them until the parents arrive and then deliver them. And it starts this sync service in the background that performs Merkle sync on every new connection and then periodically in the background, so that in the case that messages are dropped or that there were some that happened while you were offline, those will also be delivered to your apply function exactly once in causal order. And then there's the debug logs of this in action. Starting the sync service, connecting to a peer, initiating a Merkle sync, discovering a message, delivering it, logging the new Merkle roots of the two trees. There it all goes. So we've open sourced all of the components of this. At the lowest level, there's our Prolly tree implementation, which is usable on its own, called Okra. There are two implementations, one over IndexedDB in pure JavaScript, and then one in Zig using LMDB that you can use via native Node.js bindings. One layer above that is GossipLog, the libp2p service that augments Pubsub for reliable causal broadcast. And then on the very top, the ultimate goal of the startup, but not the subject of this talk, is Canvas, which uses all of this to create a framework for writing automatically decentralized peer-to-peer applications using JavaScript contracts in just a couple hundred lines of code. So if any of this is interesting to you, check out the Git repos, check out our blog post about Prolly trees, which is on the docs site here, docs.canvas.xyz. And come up to me after if you want to talk about CRDT stuff. Also, I just want to say a huge thank you to all the libp2p maintainers. It's been such a wild ride tracking the whole thing from years ago through all of the refactors, through all the breaking changes to V1. Thanks everyone for replying to my issues and fixing the bugs and everything. I really appreciate it all. Thank you.
Thank you, Joel. A great presentation. Any immediate questions here for Joel? Yeah, we got a couple over here.
First of all, thank you. That was really nice, and probably I didn't realize that it's so far ahead than what we were trying to do with universal connectivity. One question I'm really curious is you mentioned in GossipLog you're not using vector clocks.
That's right.
But you're using something like you're embedding some kind of a counter or a ticker into the key. Can you elaborate a little bit on how that works?
Yes, absolutely. Okay, so this is all in this little diagram here in the lower left. So each of these circles is a message, right? Messages are this type in the lower right. So they have a topic, they have a payload, and they have an array of parent messages that they point to. When you create a new message, the parents are just all of the heads, right? All of the messages that don't have parents in your local log at that time, right? So given this structure, given this structure, we can arrange these messages on a logical clock timeline like this. So the clock value, this logical clock value, is uniquely derived from the graph structure implied by these parent dependencies, right? So the very first message is clock 1. Every subsequent message, has an array of parents, and its clock is one more than the max clock of any of its parents, if that makes sense. That's hard to say in words, but you can kind of visualize it there, right? So then once you have this clock, you can encode that as the first few bytes of the key that you use for the Prolly tree. I didn't get into this either. One of the big differences between Prolly trees and other similar indexes is that you can use arbitrary keys for arbitrary bytes for your keys. So there are other data structures like a prefix tree that solve a similar problem, but you're constrained to using fixed size keys, and they only work if those keys have uniform distribution. So you can use it for if your keys are hashes, but then you can't do range queries for your actual keys or something, right? But anyways, so since we can play around with the key, we can create this custom encoding where the lexicographic ordering of that key, since it starts with this clock value, is a suborder of the causal order of these transitive ancestor relations. Does that answer your question?
Yes, thank you.
Yeah.
Thanks for the presentation. It's always interesting to hear about tries. So the first my question is about who will choose the next route, and can I just ignore some route which contains specific message forever and it will disappear like that, or it's some kind of protection from that?
Yeah, so let's see. There isn't any global state, right? Every individual peer has their own Prolly tree. So every individual peer has their root at any given time, right? What Merkle sync lets you do is it just lets you, given you, and then I have a connection to you, and you're another peer. It lets you iterate over the differences entry-wise in those key value stores. So I can iterate over that, and I can see, oh, I have this entry that you're missing. You have this entry that I'm missing. Oh, here's an entry where we have conflicting values for the same key. That is the Merkle sync Prolly tree abstraction. How you use that does require, so let's see. whether a peer chooses to discard or ignore or reject a message from another peer is up to them. They could choose to do that. Ideally, given an application, for a given application, you would have a agreed upon and deterministic and stateless like validate function for all of the messages, so that everyone can like agree on whether a message is valid or not and accept all of the valid messages and reject all of the invalid messages. If you don't do that and different peers have different criteria for accepting messages or rejecting messages, then their trees and their logs will kind of have lots of differences, and that will make sync inefficient because it will like discover all of those differences every time. So ideally, for an app, it will have this like fixed validate function that everyone can respect. But if a peer does choose to like skip or ignore a message, yeah, they can do that. Does that answer your question? I wasn't sure.
Since it's like friendly environment.
Yeah.
And it seems like it's timestamp index, right? This all that three.
Can you say that again?
It looks like a timestamp based index. I mean leaves, right? And it's can be, for example, synchronized by ranges 2 weeks ago. Like
Yeah, this is another thing I didn't get into, right? So we have this idea of Merkle sync. You absolutely can choose to choose to conduct Merkle sync over just a range of the leaves. So this is something like we're not doing right now, but we have in the back of our minds in the future, which is like maybe what this is really useful for is just like, peers use Merkle sync for like just the last day of messages or something. And they don't even keep the entire log around. This is just something, a reliable delivery mechanism for a certain window. And then they like archive and like ship the rest of the tree off somewhere else and like reset it. That is something we haven't gotten into like experimenting with that, but that's definitely possible.
Okay, thanks. Just one small question is about intermediate nodes hashing. What hash do you use?
Blake 3.
Which one?
Blake 3.
Oh, okay. Thanks.
Yeah.
Cool. We'll take one more question here.
I'm super glad someone is working on this. This makes me happy seeing Prolly trees. I wonder about a couple of things. I see that through Prolly trees you get like the ordering, which is really important to you. But have you looked into like what a system would look like that uses other strategies like invertible Bloom filters or parity bitmap sketches?
Yeah, I mean, I have seen, right, so there's like, yes, some of the CRDT papers I've seen use approaches to reliable delivery that leverage Bloom filters. I'm definitely not an expert in those. I'm kind of aware of them. Honestly, Prolly trees to me just seem exciting, and more than anything, they seem simple. It seems like a really clean abstraction, and that really, more than any of the other constraints, is why we chose them. It's like a very clean abstraction. Diffable key value stores. That's it. So yeah, in the end, that's what mattered to us. That's what we ran with.
All right. Cool. Thank you.